Hello, everyone. Welcome to our webinar. My name is Juliana. I am a program manager at Beyond Benign. It's really nice to see all of you here with us today. I'm going to give a couple of minutes for you to come in, turn on your audio and also video if you want. And also if you can type in the chat where you're coming from, your name and introduce you to the community, that would be amazing. So as I said, my name is Juliana. This meeting is going to be recorded. So if you have to jump off at any point, please feel free to do so. You'll have the recording of this meeting as well, and you can share with your friends, your colleagues. And yeah, so this is it. So hi, Cynthia. Hi, everyone. Hi, Sarah. Super lovely to meet you, to see you. Hi, Marta. Okay, so I'm going to share my screen. Just a second. Awesome. All right. So, as I said, welcome to this webinar. It's a pleasure to have you here. This webinar is a collaboration between the CHEMRAWN, IUPAC, and Beyond Benign. And as I mentioned, this partnership is between all of these amazing organizations. And we have here to talk a little bit about CHEMRAWN, just so you know what the committee is, the initiatives, and how you can participate. We have here Francesca Curtin. She's a professor at Memorial University of Newfoundland. She's going to talk a little bit about how you can get involved. So Fran, she's a professor of green chemistry, as I mentioned, at Memorial University of Newfoundland, and she has a global reputation for her innovative research on sustainable chemistry related to the oceans. She chairs the International Union of Pure and Applied Chemistry's Standing Committee of Chemical Research Applied to World Needs, which is the CHEMRAWN committee. She's also an associate editor for the journal RSC Sustainability and an advisory board member for Reaction Chemistry Engineering. And she received the 2019 Canadian Green Chemistry Engineering Award, the 2023 Sci Canada Kalev Pugi Award, Pugi. Let me know if I'm wrong, friend, because I definitely am, for exceptional achievements in research and development. And recently, she was recognized as one of the 3M's 25 Women Science 2024 program focused on environmental sustainability. So Fran, if you can talk to us about all the amazing things of the committee, this floor is yours.
So yes, thank you everybody for being here. And this is a collaboration with Beyond Benign and also a belated addition to the Global Conversation on Sustainability, which is an international younger chemist network project in collaboration with IUPAC. And so our standing committee in IUPAC tries to focus on projects that are related to what would now be called the Sustainable Development Goals of the United Nations. The committee's existed since 1973, so even before I was born, so it's been around for a little while. And it's a sort of outward-looking, focused group of people. Everybody's welcome to get involved, and you can chat to us. We've got a LinkedIn group going now, and you can always email me if you want to find out more or get involved. So I'll put my email in the chat in a minute, but I don't really want to take up any more of our time, because what we're all really here to see and hear about is Thomas and how to make our labs more sustainable. Thanks, Stu.
Awesome. Thank you so much, Fran. So if you want to chat with Fran, please, you can feel free to email her. She's also going to be here in the webinar. If you have any questions, you can send her a DM or anything. So it's my pleasure to introduce you all to Thomas. Thomas is going to talk a bit about greener labs and how you can make your lab sustainable. And just so you get to know Thomas, he will hopefully recently and definitely complete his PhD in chemistry on October 29th or 23rd, if I'm not wrong. Okay, during this week, under the mentorship of the Nobel laureate Ben Feringa, which won the Nobel Prize in 2016. And Thomas, he began his journey into green chemistry and sustainable chemistry then. So his research focused on developing sustainable process for the production of hydrogen and hydrogen peroxide through heterogeneous catalysis, photocatalysis, and electrocatalysis. He co-founded a chemical manufacturing startup where he will take the roles of CEO and CTO. The company's mission is to embed green chemistry and sustainable chemistry into the production of bio-based platform, commodity, and also specialty chemicals for the industry sector. And besides this whole entrepreneurial thing, Thomas, he's also co-founded the Green Labs at the University of Groningen, dedicated to making laboratory practices as sustainable as possible. And in collaboration with Martin Farley, he now advises institutions and companies worldwide on improving laboratory efficiency and sustainability, reducing costs and CO2 emissions. Thomas is also an ambassador of Beyond Benign's Green Chemistry Commitment Program, and he's helping to increase the awareness of green chemistry in higher education institutions. So Thomas, I'm gonna stop talking. The floor is yours, and thank you so much for being here with us today. We're excited.
Yes, thank you. My God, I always think these introductions are super long. So yeah, thanks. We could have done it super short, but let's see if you can see nicely the screen here. Let's okay. So is this full screen and nice for you to see, guys?
That's perfect.
Okay. Yeah, so my name is Thomas. Thank you for the invitation. Yeah, you introduced me already, so I will keep that short. That's me. I'm at the University of Groningen in the Netherlands in a group of Ben Veringa, and this is the building where I work in. It's here on the 9th floor. This is my laboratory, and the shape of the building resembles a DNA strand. So it's mostly the biology building, actually. Yeah, and the Netherlands likes to design sometimes. The architects here like to design these kind of nice buildings. My focus of my PhD indeed is sustainable and green chemistry, where mostly I was conducting photocatalysis and heterogeneous catalysis, or both in combination, to make energy carriers, so hydrogen and hydrogen peroxide indeed. And we also do biomass conversion and making coatings and polymers from that. And the real reason why I'm giving this talk is about this. So green laboratories, sustainable laboratories, green labs in general, sustainable lab practices. I will talk and dive more the importance of that today. And at this university in the Netherlands, I'm the LEAF coordinator. This is like an accreditation framework. There are 2 at the moment on the world that you can do. It's LEAF or My Green Labs. And basically, you can get an official accreditation, but you do not necessarily need to have that to make your lab more sustainable. You can just do it yourself. Everything is open access. All the recommendations of both systems are open access. You just need to find them in nice publications, and then you can do it yourself without that. Why is this important? So most of us, hopefully, or at least for myself, we are scientists, and we want to find out things about nature and learn things and create new things and good things for the planet. Also, my supervisor sometimes, I guess, wonders about rotary evaporators and how they work. And this is a funny photo shoot that he always needs to take part of on sometimes. And generally, we want to make the world better. And we want to make the world better because we need to improve the sustainability of every aspect of our life. And this can be done through research projects. And then mostly the main things that come to everybody's mind are, of course, these 3 here, the bottom right. Let me actually go to the pointer. So energy transition, feedstock transition, or material transition. These 3 are quite obvious that these are related to improving our future and making our humanity survive the climate crisis. But then, of course, there are also fundamental research projects that are important for as foundation to these other 3. So it's not, it's for human health, for example, engineering, materials, things. These are all important as well. Otherwise, these 3 are not possible. The second pillar of sustainability in science, so next to the research project, is the education. So that we teach future students and basically scientists how to work and apply sustainability and think critically about sustainability. And then one aspect, for example, that many people use and talk about is the 12 principles of green chemistry. And if you educate those nicely in the bachelor and master's courses, these will be then automatically applied to the research project, and then both together are becoming then a nice future. The third pillar is basically how these research projects and also the teaching is conducted. So this is then how we conduct these things in the labs ourselves. So this is then about how much plastics and chemical waste we generate, how much water we are using, electricity. So basically the things that we are trying to reduce at our homes, how can we improve our workplaces in a way that they are going hand in hand with our goals of our research and also of our education. And the talk today will be mostly focusing, of course, then on the blue part and the third pillar of this section. So we published everything in RSC Sustainability, which is a review that we published, and then also expanded that review with our data from our university. And everything that I show you now is seems like a nice approach and everything was nicely laid out, but it actually went the other way around. We started as a grassroots movement here at the university. We just started things. We did things ourselves without talking to anyone. We just turned off lights more and all the things that I will show you soon. And then over the time, we became so big that we got access to data from the university. And this is then, for example, the data that came out of it. And just to stress, many people think that you just need to start with these data and have this data to make the labs more sustainable, but you can just do it already without the data right now. And this data will come along as soon as you get more recognized, or if there's a grassroots movement or people who do things, you will get more connected within your institution, and then you will get access to people that work on this themselves already. And at our university, we have, for example, a green office. And this is the carbon emissions per category of the whole University of Groningen. So in blue, for example, you see the electricity consumption. In red here, you see the gas consumption. And then here you see the COVID crisis had a dip, of course, because commuting, which is light blue, or green air travel here, which was not taking place then in 2020, 21. That's why you see that here. Also here, the marked stuff. This is carbon offset electricity, which means the University of Groningen buys carbon certificates to reduce the emissions of their fossil-based electricity. And of course, me being the scientist and the critical person, I didn't want to publish it like this, that we are now very good. So I didn't accept their electricity offset and just marked it. But generally, carbon offsetting in any institution or company in the world should just be maximum a transition thing and not like a solution. You actually still need to reduce your scope 1, 2, or 3 emissions. And then you can use these as a transition period, but often these should not be the solutions for sure. Zooming in, so this was the whole university. Also, by the way, including waste and food in the canteens of the students and the waste here. Also chemical waste, it's orange and yellow. Here you see the yellow, that's the food waste, but orange, it's very top here. And you cannot really see it. It's so little in comparison to the CO2 emissions that our gas for heating or the electricity consumes. And if I zoom now to my faculty, so this is the science and engineering faculty. So where biology, chemistry, life sciences, physics, engineering, mathematics, computational science, all these STEM sciences take place. That's the Faculty of Science and Engineering. So it's also written here on the top right, FSE. And here we also got, for example, the gas consumption, and our team started in 2021. And I would not dare to say that there's a significance in gas going down, even with our Green Lab work already taking place. This can be just an artifact, for example, of the energy crisis because of the war between Russia and Ukraine. There was a big energy crisis and people started talking more here roughly about energy, and then people use less of that. Same for light. So electricity consumption in laboratories, nothing really is changing since 2014. Also this, I would not dare to say that it's anywhere near where we should be able to reduce things. Roughly the Faculty of Science and Engineering, we have 1,800 employees there, mostly, so these are active lab researchers, the 1,800, everybody doing research in the laboratories there. These laboratories consume per hour the same amount of electricity than a Dutch average family of 3 to 4 people per year. So every hour, a family energy consumption that they do a year. Just to put in perspective how much more electricity institutions with laboratories use. That's not universities only, but also companies. Showing this, what I just showed you in numbers now. So the whole university has different scopes of emissions, and then here with or without the offset. Let's just talk about without the offset here at the moment. So we have 60,000 tons of CO2 emissions at the whole faculty, at the whole university, and the Faculty of Science and Engineering has 26,000. So half of the whole university's emissions come only from one faculty. And as I said, there are 1,800 active lab members working, and the problem here is that the university has 10 other faculties. So from point of view as a company, let's say the university is now a company, 10 faculties are using the same amount of energy and electricity than the other one where the laboratories are located. And that's why it's also smart of a business point of view of the universities or anywhere where we are having companies that are focusing on science related things with laboratories, that we start reducing our emissions there, because it makes sense from carbon point of view, but also of course business wise. At the Faculty of Science and Engineering, we published in 2019 390 publications. So this is among all disciplines. This includes again chemistry, physics, biology, life sciences, neurosciences, all of it. And there were 390. So now what we could do then, just to show people what's the impact, is that per publication, roughly the embedded footprint here is 68 tons. There's also some other literature available, but you can say for yourselves, wherever you are now, if you publish a paper yourselves, roughly you can say 70 tons of CO2 are embedded in that paper through the energy or chemical consumption, whatever you do in your lab, roughly 70 tons. Per person per year, us as researchers, that's between 10 to 37 tons, depending on the discipline per year. So for example, astronomy uses much more than biology because they have high computing facilities. But just to put these two numbers now in perspective, the annual emissions of a person in Ethiopia is 0.5 per year. A car driving 12,000 kilometers is 2 tons per year. And the Paris-aligned budget that we have to reach 1.5 degrees per person per year is 1.5 tons. So you see already, excluding our private footprint, only our work-related footprint is much higher. And let's say, I don't know how many papers we all or you publish, but you can think of this yourself now. Also in the past, how many papers you co-authored. That's the footprint that is exceeding where we should be. And that's, of course, a big problem. This goes then also, of course, with conferencing and traveling there by planes. Of course, depending on the country size and everything, train travel and flight travel ratios are a little bit different. But for our university, again, we are, of course, also our employees fly to conferences. And the Faculty of Science and Engineering here, these are all faculties again. So here you see 1 faculty, 2, 3, 4, these are all 11. And FSE, this is ours here. This is the one where I'm located. And yeah, indeed, we are flying less to conferences now over the years, but it could be also related to the COVID crisis, etc. Our faculty, the employees there, usually travel to Italy, USA, and Spain per year. So these are the most visited destinations. And our faculty is located already in Europe. So we fly within Europe, where the train system is quite good. From the Netherlands to Italy, for example, or from the Netherlands to Spain. Of course, if you go overseas, that's a different story. Roughly, our faculty, all the people there are flying, and were flying in 2022 148 times around the planet or around the globe. We are around 8.4 million researchers on the planet. That's 0.1% of the population. So we are not many scientists, actually. We are a very high society class of people, actually, although we don't think of us like that regarding money. But if each of us just travels to 1 conference per year, then our scientific footprinting footprint of scientific conferences is bigger than of countries such as Uganda. So what I want to say here is, even if we are not many people, we are still contributing quite much with our flying to the world's CO2 emissions, and that needs to change for sure through, for example, online events like this. My supervisor is, of course, a person who flies very often because of the Nobel Prize. And I didn't ask him about this for this data. I just went to our secretary actually and said to her if she can make me an Excel document of his flying from January 22 to July 2023. So 1.5 years roughly. And then I drew this graph and wrote the manuscript, and then I just gave the paper to him, and then he saw his footprint. I didn't ask at all for this. So and then he was quite surprised. And now the outcome of this is that he's also declining invitations more, but or attending online and traveling by train much more. Generally, Ben is flying 3.5 times per month. So this is basically 2 destinations. So back and forth, it's 2 flights. He flies 42 times per year, and that's 26 tons of CO2 per year. With all his papers he ever published in his life, he has emitted 320, oh no, these are annual emissions, 324 tons of CO2 per year. So his flying only corresponds to 8%. And that is a Nobel Prize winner who's flying super often everywhere, because he's representing science and scientists also for politics and policy makers. Nobel Prize winners are always in different meetings than the usual scientists. So they are invited to many policymakers meetings as well. And that flying footprint is so little in comparison to his research. So you see already that the research is a very big factor again. The water uses, for example, in comparison to office space is 5 times as much. And at the university, the water footprint is 60%. So all the water consumed in laboratories is roughly 60% of the total water consumption of a university. So it's all companies that have laboratory research. And this includes also toilets and everything, by the way. This means our cooling of reactions, or however we do it, is much more than the toilets of the whole university, for example, or the sinks where we wash our hands, make the coffee, etc. Energy, so a lab uses 10 times as much electricity than an office space of the same size. And roughly, as I already mentioned, 60 to 65% of the whole university's energy bill goes to this one building, or let's say 3 buildings where the laboratories are located. So laboratories then, of course, are using much water and electricity, but then we have another problem, single-use plastics. Roughly, you can say all the laboratories on the planet produce about 5.5 million tons of single-use plastics. This corresponds to 2% of the global plastic waste comes from labs. And then again, think about the fact that how many researchers are on the planet. That's not very many humans, but we still correspond to 2% of the global plastic waste consumption comes from just these facilities where a tiny amount of humanity, let's say, works. So we did a study at my lab, actually. We were 3 researchers for 5 months in a chemistry lab, and then basically collecting our gloves and syringes. And of course, these are all contaminated, these 2 parts. But this is just a wrapping paper of the syringes, for example. This is not contaminated at all. As I said, the faculty has 1,800 active lab researchers and around 3,000 employees with the people working in the organization. So we produce roughly at the whole faculty 9 tons of gloves per year, 4 tons of syringes per year, and 4 tons of packaging material. So these are all 1,800 lab researchers. This is an extrapolation from the chemistry lab to the whole faculty. And you can use a chemistry lab quite nicely as extrapolation, because biology uses, or life sciences uses, much more plastics. But for example, physics or maths or computational science uses, of course, much less. So a chemistry lab is quite nicely located in the middle between high amounts of plastics and no amounts of plastics, because chemistry still uses quite some glassware for pouring things and etc. Roughly 70 tons of plastics is produced at our faculty. Let's go to teaching of students. Teaching of students, so we were following our educational laboratories for 6 months, where we had 1 or 2 courses running of about 2,200 students. And these 200 students used 52,000 gloves in size L, 57,000 gloves in M, but also this one here, this is quite nice. This was the red numbers, 2 weeks biological related practical. They used about 40,000 pipette tips by 200 students in 2 weeks. So, and there's no research outcome here. Of course, we are just teaching them about, for example, gloves are quite important regarding safety, but we need to think about how we educate our students as well. I will skip this biology research lab, but this is a biology research focused lab and they produce 500 kilograms per year. But a EU resident, for example, per year uses private footprint. So this is then basically me, my own plastic in production is 35 kilos per year. And you see already that you double basically with these 17 active researchers, you double your plastic footprint on the planet because of your work. And depending on what's your research, you can of course have bigger numbers like 500 per person per year instead of just 31. For us in the chemistry research, at least where I'm from, our focus is a little bit more the chemical solvent stuff, and we have much more solvent waste. And this is then also the solid chemical waste. And this is then here the solid waste of the University of Groningen at the Faculty of Science and Engineering. You see really, so although the communication about sustainability increases, nothing decreases here with our waste. Actually, it's doubling almost from 2019 to 2022. So nobody really, I mean, we publish papers in green chemistry and ACS sustainable chem and engineering, but nothing here is changing. Research is growing, more papers are being published, more scientists start, etc. So the scientific community grows as well. So roughly what you can say now, at the University of Groningen, 109 tons of hazardous waste are produced per year and 70 tons of plastics annually. And I can now basically split it up to chemistry building and biology building. So this building here, NB4, that's a chemistry one, and this one, NB7, that's the biology focused one. And you see the chemistry problem is here, the solvents and not the plastics. Whereas biology has the plastics as a problem, chemistry has the solvent waste as a problem. And for example, in my research group, per researcher per year, roughly 150 or 160 kilograms are produced per researcher. And in student education, mostly students use acetone or ethanol to clean their samples and everything. So mostly they produce the waste acetone and ethanol, and that's roughly 100 kilograms per year. So what you see here, research in chemistry has a little bit bigger solvent footprint or hazardous waste footprint than what education has. And another nice thing to know, science education here at universities, the students consume there roughly per day an average of 23 gloves, 7 pipette tips, and 260 grams of hazardous solvent waste. And 23 gloves, that's basically, let's say they have 2 hands, so then they have 12 or 13 gloves per day during 8 hours, or let's say 6 hours of a research practical. So that means roughly, more than once per hour, they change their gloves because of cleaning, because of toilet, because of they cannot touch this machine with gloves. So we teach them safety very excessively, which is super important. But we need to basically think about how we educate the students regarding gloves as well. And I will come to solutions soon. One solution is, for example, the laboratory efficiency assessment framework from the University College London. This is LEAF. But as I said, you can also use My Green Labs, but you can also just don't do neither and just look online on publications, and you will find all these recommendations. They are written down, and you can just do it without, because here you need to pay, of course, for both of the systems. You pay access to the software. I will not go through detail here now in these categories because I will guide you through it with pictures. So one recommendation is is of course about fuel hoods. I didn't talk about fuel hoods at all yet, but the electricity consumption of a lab is so high because every 6 minutes we basically replace the whole air of the room through our fume hoods to keep the humans inside safe. And one fume hood uses roughly the same energy as 3.5 households. So that's basically 3.5 houses, or people with, let's say, 3 to 4 people living there, the average. Then you can think about how many fume hoods you see at your institutions. And then basically you can think about how many houses are basically standing there in this small area. And just closing them from half the stand to full stand already, this is super obvious for safety, etc. But already consumes almost 70% less energy then, because the flow rate decreases. Sometimes they are automated, so often you need to pull them down yourselves. But just that is reducing the energy footprint of this equipment quite drastically. Same for -80 freezers. So -80 freezers consume roughly 2.7 times the energy of a household, depending on what temperature is set on. And basically what you need to do is to increase the temperature from -80 to -70. It will not have any effect on your samples, because there's also much research already published on that. And if you do that, then they reduce the energy consumption by 30%. So by that, you save already quite some electricity by these two actions if you communicate this nicely. And you have quite some households that you can save the energy bill with. Going to more electricity, some chemistry labs have rotary evaporators. There's this machine here, where there's here a bath of water inside. And then basically, you can distill solvents from one side to the other. But if you cover this bath here with these plastic balls, basically like in Los Angeles, where the freshwater lake is also basically covered with these black balls, first of all, you reduce its evaporation, but also it stays on the temperature where it is. So if it's warm, you can turn it off, and then basically it's staying at the temperature and the warmth. Also, this whole thing doesn't need to reheat all the time. And roughly, you save 56% of energy by that. Many countries use these already, but especially in Western cultures, it's less of a practice in many locations, at least, because because there was more funding and money available. So that it wasn't a matter. But let's say where at locations where there's less funding available, it's quite often already normal practice to do this. And that's in general for all the things that I'm saying here. There may be locations on our planet where things that I say that are sustainable in other laboratories are standard, because the way they grow up in the culture, and of course the funding allocated to these locations and institutions is much less. So they have less money available, and then they work more sustainable automatically. So it's sustainable is a new word that came up, let's say, in the 5 to 10 years. But many practices, especially in labs, are already standard since 30 years at different locations, and nobody mentioned ever that this is sustainable. It was just more economic. Life cycle assessment is a very big thing. We need to basically ask our suppliers when we order things, we need to ask them for a life cycle assessment for our Eppendorf pipettes, for everything that we order. There's, from the My Green Lab page, the ACT label, where you can already compare the sustainability of different products. But basically what you want to see is that the culture of the suppliers also changes. So they start reducing the embedded carbon in their products. So the whole basically system changes, and it's only changing if we as customers ask the suppliers for life cycle assessment, and then they start rethinking in their marketing departments. We wrote a guidebook which everybody needs to read in the beginning, in addition to the safety thing. And we hang stickers, which people, I have to admit, get blind to over the 3 years now. So we have to redesign things or need to remind them more. But basically, switching off things is very important. And you can do that nicely through stickers, but also guiding them with a guidebook immediately through a nice start in the lab. Everything should have standard operating procedures. So this is super nice and important, because let's say if a reaction doesn't work nicely because you were not able to run with the equipment and machine properly because you didn't have a standard operating procedure, that means you need to redo the experiment, and that means you regenerate waste which you could have avoided. So standard operating procedures maybe seem annoying and maybe don't directly translate to sustainability, but by having reproducibility issues, then what you have is you will generate more waste, or somebody reads your paper, cannot reproduce you on the planet, and then basically you generated waste even in a different country because your supporting information or standard operating procedure was not written nicely. Sharing equipment is also very important. Many universities and institutions do this already, but it's important that the culture needs to a little bit change. Also funding, how funding is allocated. It needs to be changed that a machine that is bought from a specific project code that is only belonging to this PI and this one project code, and nobody's allowed to use it, because we can avoid embedded footprint, of course, of the machines, that not everybody needs to buy their own centrifuge, but by basically sharing all the equipment that we have, fridges, freezers, and you generate a collaboration atmosphere between PhD students and postdocs and everyone really. And you also save money, of course, on the machines that you don't need to buy anymore. So now going to chemical waste. Chemical waste is a difficult one because many people have them just open like here in the fume hoods, but then not with these funnels that are closed. Just a normal funnel where everything evaporates every night and day into the atmosphere. And there are, of course, quite some nice greenhouse gases in these all the time, which just generate more global warming 24/7. So having just these funnels closed and then you already reduce the evaporation of your chemical waste very much, and that's very important. Reducing the plastic waste of weighing boats. So these are plastic weighing boats. What you can do there is you use the backside of the parafilm. So basically, some labs have parafilm and then you wrap something, but the back paper, it's a nicely waxed paper, which is not electrostatic. You can just use that paper instead of throwing it away, and that's your new weighing paper. Or you use glass weighing boats, which are super convenient actually for starting reactions. Everything uncontaminated, also lab waste. This means also the packaging of syringes and everything goes into this plastic one here. So basically uncontaminated plastic waste goes here. These are what you see here in this box, and also same for paper. Uncontaminated paper, for example, from washing your hands at the sink, and then you're drying that with paper instead of a normal towel. That paper goes in here, and then you can just put it there. Then you have, of course, glove waste and syringes and paper that is still contaminated. There's no real solution on the planet, by the way, at the moment, but there are some startups starting that want to work with recycling and circular gloves. Same for syringes. And I would say in the next 5 years, there will be really nice solutions for these coming. Also here, waste canisters, you can just reuse, instead of buying new fresh waste canisters for your solvent waste, just reuse the solvent bottle from your where you got your solvent delivered. And when that one is empty, you delabel it and use this very same propylene or polyethylene canister as waste canisters. So you don't need to buy new waste canisters anymore. And then you have them for yourself. Next thing, sharing chemicals is very important, because many universities have already a sharing system, but many also don't. And then you basically need to start sharing chemicals only among your group members with an Excel document, because it's your own project code. And the problem there is nobody knows what they have. Sometimes you order expensive chemicals that could be available in the next door in the lab. And you should just start sharing chemicals, because it has many advantages. First, you don't need to buy it, and you can start immediately often to do the reaction that you just read about in the paper. You can just do it immediately because the chemical is already there. You don't need to order it. Same then for right sizing experiments and not buying too much. So please don't buy always a 1 kilogram pot of whatever chemical or 500 gram of a chemical, because it's cheaper per gram to buy a bigger amount, although your research project maybe could be finished with 200 gram. Because in the end, if the money that you save there on your project code by buying more per gram will in the end just add up to a chemical waste after 5 years or 10 years in a graveyard of a chemical storage that you have in your labs. Nobody uses or trusts these chemicals anymore at some point because they have like these crusts on the top. They are these yellow, dirty flasks, and then you need to throw them away. And then again, by the way, your same project code that your PI had, that money, that still goes away for paying the waste. So the money, the nice intention with saving money often can go a long way. And you don't think about that because you're already gone with your research project in a different institution. But right-sizing chemistry as well as sharing chemicals can also overcome this because the chemical pot that is maybe old or not too full, you share that, and then basically somebody else can empty that pot, hopefully, before it's thrown out. Yeah, so we started in June 2021. And yeah, we joined in the LEAF framework, and we got then an accreditation. And this accreditation is really just nice often for the universities themselves. I mean, I do it myself because I believe in it and it's important and it saves CO2 emissions. But for the university, it's nice because it saves money. And for the university, these things, these labels are nice because they attract students. Then they get more student tuitions, and the students pay, of course, their fee. And maybe you basically have a marketing tool for the university. So but doesn't matter if it's for a university or a company. Many people that don't work in labs, they care about these certifications and they care about money. So often sustainability and carbon reduction goes hand in hand with these things. And it's just this nice way. What you need to learn is to start communicating this with the stakeholders and understand their point of view on things. And that's why for some, it's nice to have these certifications, but you can do it without totally. If you close everything nice and heavily during your 2 weeks winter break, let's say during Christmas, we save, for example, 250,000 euros in these 2 weeks only. We have also recommendations for the digital lab spaces, of course, but I will not go into detail there. And these 46 labs that have at the moment an accreditation, they save the university roughly per year 400,000 euros, as well as 500 tons of CO2. So for me, again, this is super important, but this can be very nice because here, what we are at the moment busy with, let's say 400,000 is saved at the faculty. Now we can create a funding again, where people can apply for only if you have this label, let's say, then you get more people joining your label. And then these people can apply for a fund for new equipment, for a new freezer, for a new something that's more sustainable. And then they get equipment and have access to a money pool because they work sustainable. And then it's basically, yeah, you create a society and a community like that. Difficult again with this 400,000, it is that it goes to different pots. So it's electricity, water, chemical waste. It's not like there are 400,000 on one bank account. It's like 400,000 spread around everywhere. And that means nobody really can see this money or has easy access to it. So you need to, that's why it's difficult for us at the moment to create this fund, but with nice communication it's possible. Yeah, and then we published all of this, and this is generally, this was a grassroots movement where we started with a group of people having coffee and wanting to make our own research better. And yeah, basically, if you do it yourself, you can start per room, roughly 9,000 euros and 10 tons of CO2 per room. So per lab room, let's say, that you have. And the importance of all of this is because in the end, we are scientists and we want to make the world better. But with our research, we have an impact on the planet, and which is very bad, although our intentions might be good, especially if we are green chemists and chemists focusing on sustainability goals. So we need to apply these green lab practices ourselves, because only if we are doing it, we can be a nice example for our friends or family or really everyone, because it's important that we as scientists start this movement and really take part, because we cannot expect that industry or politicians or really anyone's changes in society if we as scientists also do not change ourselves. Thank you.
Great. I see lots of applause going on. So
I will keep sharing. So if you have questions,
in case you go back. So just first of all, just to say thank you for all your insights, the statistics and the links to kind of line up, you know, how much is the CO2 footprint from a lab compared with everyday items such as somebody's household or a car and so on. And the practical advice. So there was a comment in the chat from Olivia saying that she hadn't thought of using the back of the parafilm as waypaper. So she'll be checking one out soon. So
nice.
I'm going to ask a few questions that have been posted in the chat. So Cynthia Melegre said, I've noticed that several solvents considered not recommended by various guides, such as diethyl, THF and pentane, are still used in a lot of teaching labs. Have you seen anything on replacing these, or, you know, is it a case of some resistance to replacing the experiments? Are those teaching experiments really needed?
Yeah, so luckily for us, the main coordinator of the teaching labs is also, I convinced him to join also our Green Lab team. So he generally improved all the experiments among several courses. So first semester, second, third, and also to masters. He basically changed them to talk about lab sustainability and the 12 principles of green chemistry. And let's say a product that a student makes in his first year is a starting material for a student in their third year for a different experiment. So he started to intertwine the courses with each other, to have the products that are not usually thrown away as starting materials for a different course, let's say. And then regarding the pentane and everything, very good question. Many discussions that I had with about this already with him. So often it's recommended indeed from these solvent guides to use heptane instead of pentane, for example, because it's not evaporating into the atmosphere, and therefore you have less safety issues, but also carbon impact because of the greenhouse effect. If you use pentane for all the experiments or columns, for example, instead of pentane, what you have then is that it's evaporating, for example, slower at the rotary evaporator. And then what you get is first a student queue of that are waiting for the pentane more. Second, the rotary evaporator uses more electricity to evaporate heptane over pentane. And then we calculated the life cycle assessment of changing the pentane to heptane, if it makes sense from an electricity point of view, and to do that, and if it's where the costs will end up, and the whole CO2 impact of the whole process, the whole system basically. And then in many situations, often pentane still can be a good choice, especially in teaching labs. For research labs, of course, heptane all the way, but for teaching, pentane can be still nice because it evaporates fast from one side to the other, and then you have less electricity consumed and heat.
No, that's a really good idea, and it's also important that we think about, to a certain extent, the research labs and the teaching labs having somewhat different priorities needs in terms of making them more sustainable. On a related note, Vijay Shah asks that sometimes it's hard to overhaul an entire curriculum. People say it's too much. What would you recommend as far as an order of operations for greening labs? So he also says, what's the easiest place to start in your experience?
To be honest, the easiest way depends really where you are working. So for me, I was a PhD, or I still am for 2 weeks, candidate. So I really just started in my own lab with with people that were around me, and we just did the things ourselves. It starts easily with electricity, turning off equipment, or having equipment turned off as default in your lab instead of turning it off after use. So basically the lab should be always off at default mode, and then you turn things on when you need it, like an oven or whatever, or also pH meter. And then, but for teaching, I indeed would not go directly for curriculum. I would do the same things there. So teaching labs, of course, often already have many things off when the students are gone. But teaching the students, for example, regard how to use gloves or plastics or weighing boats. You can start with the weighing boats. That's an easy thing for the students to see. So you create awareness for the students. And when they become bachelor or master students, or PhDs, they go to research labs, and then if you teach them nicely directly on lab practices, then they will carry that through to the research labs automatically. So I would not directly change curriculum. I would just change easy practices that are not related to the experiments at all.
Yeah, no, that's great advice. I'll also just promote the green chemistry teaching and learning community of Beyond Benign. Yeah. So there are some discussion boards there. So when people get to the stage where maybe they are thinking of changing the curriculum a bit, or they want to know, you know, what labs actually work well that have been developed and shared previously, that might be a good place to look.
Yeah, there are many resources on the curriculum, on experiments as well. But that can be a difficult step, and you need to decide what's best for every institution. Yeah.
And seems we're on the topic of institutions. Another question from Cynthia is, and I think probably one that a lot of people have, is can you comment on where people get money to pay for the accreditations? Is it normally the university paying? If so, how do you convince them? And in some cases, is it the PIs that are paying out of their own pocket or research accounts?
Yeah, so for us, the university pays, so our Faculty of Science and Engineering pays, and the reason for that, or how we did that, was I went to the faculty board or the board of the university, and I just gave a similar talk to them like this, and then you convince them quite easily to invest 3,000 euros, for example, to have access to an accreditation software per year, when they see that you save them around 1 million per year. So the initial investments should come from the university or the faculty or the institution, but not from each PI, for at least for the accreditation software, because you want top-down support from the institution as well at some point. And in the end, you are saving their money, so it's also a business case for them. So usually it's quite easy to convince them, to be honest, when you lay out the numbers properly.
Yeah. No, I'm thinking that maybe somehow in the future with Beyond Benign, maybe it's something we need to work on, a pool of funding for regions of the world where maybe they're not going to have the funds to pay for the software and accreditation. That
for sure.
I don't know if it's something that maybe in the future, you know, Merck, Millipore or somebody else might be interested in sponsoring, and then people can apply for grants or something.
Yes.
Okay. I think we've probably got the time for one last question that somebody posted on the discussion board. This is again from Vijay Shah. It says, I noticed with the particular example of pentane versus heptane that there's a potential compromise between worker safety and climate impact. Is it possible, do you think, to aim for safety first and then look for deeper solutions to climate impacts?
Good question. To be really, really honest, so generally all these recommendations should go safety first, research second, sustainability third. Research should never be impacted by your decisions on sustainability, let's say the outcomes of that. If you need to use an amount of solvent or anything, then you need to really do that because then your supporting information is nice, really written, and then your reproducibility increases, and then that is more sustainable for another researcher. But safety, of course, is the most important, even before your own research project. However, all of the three, to be honest, although I mentioned it in a scale right now, they should go, they should be the same entity almost. They should not be seen separate. I feel always, for example, safety is so embedded in our work that it's just a normal thing that we accept is so important that we don't even question it. And I think that's what we should get also with sustainability and in collaboration with our research project. It should be all of the things at the same time, but it takes a behavioral and mindset shift. And one thing doesn't exclude the other. And it's not about compromising things. There's only the one best solution, which is safe, good for the research, and sustainable. And one should not be more important than the other in the end. However, I see that in the process to go there can be indeed priorities.
Absolutely. Yes, I think that's a good point to end on there. Juliana, did you want to add anything at this point?
I just wanted to say thank you all so much. That was lovely. I love the questions. I love the initiatives. Thomas, we really appreciate your time being here. Fran, thank you so much for moderating our question period. Thanks to all of you for being here. And as Fran said, if you have any questions, if you want to continue the discussion, please join the GCTLC platform. And you can ask questions for Thomas there too. He's also there. And also, we're happy to see you in the other opportunity. And please continue the discussion so we can make the world more sustainable, because as Thomas says, we have to. So if we don't, who else is going to do it? So thank you all so much for being here. And I hope you have a great rest of your day, evening, night, and all these things. Thank you.
Thank you, guys.
You.
Bye-bye.
Bye.